can I start or? Okay. Okay, good. Thank you for coming to the second part. I'm going to take a different direction now, and I'll try and explain why or how is all of this even related to celestial holography, because that seems to be the beef which everyone is interested in. In fact, for a large part in this talk, I'll talk about a simpler space-time, which I hope people are familiar with, which is ADS, and try and motivate holography from there, which is, I think probably most of you know better than me. And everything that I said in the first part can be forgotten for the large stuff in this second half of the lecture. And I left out some derivations about the symplectic structure and so on, but I was told that there's a discussion session, so feel free to ask more questions related to that and how we got to the charge and so on. But for now, I'll be switching gears, and I'll talk about something completely different. And it will introduce the subject of the principle of holography of information. So this is work which has been mostly pioneered by Subrat and many other people, including Alok, Latha, Pushkal, Siddharth. And many others, but most of the recent papers have been written with them, along with some papers which I wrote as well. And a good review for this, I don't know the archive number, but Subrat has some set of lecture notes where you can find some good review of all of this. So what I'll do in this lecture is try and motivate a large part of whatever Anirban is going to talk tomorrow, or maybe the next day, and why, and as to how or where the celestial holography should live. That's the thing I'll try and motivate in these two lectures. So I'll first actually start with ADS spacetime, since I believe that's more familiar to everybody else. And later I'll talk about flat space and how some of the things that we discussed, like the supertranslation charge and so on, how they play a role in understanding these things. So, okay. So the basic idea is that if you have ADS spacetime with some set of fields in the bulk, then as you all know that we can write down the boundary operators corresponding to fields by this manner. Where this delta is the conformal dimension of your field that you're working in. For example, if you have scalar fields in the bulk, then this delta has an expression of this kind. Okay, and everything that I'll talk about, I'll set the ADS length scale to 1. Okay. Now, firstly, let me tell you something which is kind of obvious, and that is the statement. Suppose I have some bulk excitation in here, starting at, let's say, the point t equal to 0, r equal to 0. Then what I'd expect to do is if I wait for a sufficiently long amount of time, like let's say there are certain observers, call them set of observers A on the boundary, and if they wait for a sufficient long amount of time, they'll be able to see what is going on in the bulk. Okay, that's just from causality. So if there's some excitation in the bulk, we expect that once light rays have traveled from there, the observer outside will be able to see what's going on, right? But from the intuition of ADS CFT, we know that there must be something more that's going on. What we expect to actually understand is this observer who's living here in this particular time slice, call it t equal to 0, probably has information about the bulk state at t equal to 0 itself. Okay, that is what ADS CFT would tell you. that everything which is available in the bulk of ADS, the CFT already knows about it, CFT which is living on the boundary time slice. Okay? But it's not clear as to how this principle is working from a canonical gravity point of view, or let's say without invoking any principle of string theory, how do you exactly go to this statement? Or how do you realize this in some observational way? And this kind of principle is basically trying to resolve that for us. Okay? So what we'll aim to do is that we'll first talk about how anything in the bulk can in general be expressed as some sort of boundary operators. Okay? By boundary operators as in things which can run over some arbitrary time. Typically it's the so-called light crossing interval, which is basically a time interval of pi in the unit cell ADS equal to 1. And then what we'll argue for is that by using the usual principles of canonical gravity, everything that the observer could have perceived by waiting for 0 to pi time interval, he or she can also perceive it by just waiting for an epsilon time interval. Okay? Is that statement clear? Should I repeat it? I should repeat. Okay. So what I mean is as follows. Let us say there was some excitation in the bulk, like this, and if there's some observer A here, if that person waits for time period of t equal to pi, then that person knows about this state. Okay? The person will eventually get to know what excitation was caused in the bulk. However, what I'll try to convince you is that if the person waits for a time interval of epsilon, where epsilon can be taken to be 0, any small finite number, then that person would already have information about the state and why it does not violate causality.
So you're talking only of pure ADS?
I mean, you can have excitations on top of pure ADS, so what do you mean? The excitations I'll be interested in would be of the form some operator X acting on the vacuum state.
Why one needs to convince that this information will be the observer will get to know about the excitation? Because if you start from ADS CFT?
I'll not use any ADS CFT in this argument. I'll not use any string theory, and eventually we would like to understand what the analog of this is in flat space. And by developing these principles in ADS, we'll see how these principles can be extended to flat space as well. Because the entire program of celestial holography is to try and understand if there's a dual CFT construction for anything that is inside Minkowski, but it's not clear as to where the CFT might live. So what we'll try and look at in this lecture is give an intuition for where the CFT might live without invoking any principles from string theory. Okay, any other question?
Are there constraints on epsilon?
Epsilon can be anything which is non-zero and tiny as you want it to be. It's something which is non-zero. The exact ADS CFT statement would be for epsilon equal to 0. And probably that setting epsilon to 0 would require some inputs from string theory, but we do not have that yet.
Exact ADS CFT means you don't have the excitation.
Oh, no. By exact ADS CFT, I mean what ADS CFT teaches you is that everything would be available on the same time slice. But here I'm saying that I need a thin time band. In a sense, I take a time band of window epsilon. You can set epsilon to very close to 0, as close as you want, but you cannot set it to 0 with the proofs that we have.
So the t equal to pi time is a statement of what?
Causality. Because that's just a light crossing time in ADS. So if you take ADS, if you take global ADS, and if you wait for t equal to pi, then everything which is at the center of ADS would reach the boundary.
Come from causality to the exact safety
statement. In a sense, yes. So if you allow the observer to wait for t equal to pi, some pi units of time, then they would anyway know about all of this. So anyway pass because of causality. But now what I'm trying to tell you is that the theory is more constrained than that. But just by having gravity in your theory, all of this requires gravity, by the way. All of this requires dynamical gravity. It does not need string theory, but it needs dynamical gravity. So by allowing yourself to have dynamical gravity in your theory, you'll be able to do more than just wait till pi interval. You'll be able to say everything from just this epsilon time interval.
These statements are held in ADS3 also, right?
This statement is valid in any ADS, yeah, ADS3 also. I'm not sure about ADS2, but ADS3 for sure. Yeah. By dynamical gravity, I don't mean dynamical gravitons. I mean, you should be able to measure the energy as the metric fluctuation at the boundary. That's the thing I mean. I'll come to what I mean by the dynamical gravity and where it enters. Okay? So the main thing that will go into all of this is that, or one of the main principles that goes into all of this is to use the fact that the Hamiltonian is a boundary term. In a theory of gravity, the Hamiltonian is a boundary term. We had seen an avatar of this in the previous lecture, where I had written down this general QF. I'll come back to this example again. But this, as we saw, could have actually been written as a limit of this particular metric fluctuation, the Bondi mass aspect, at u equal to minus infinity. So in that case, what happened was this guy was a metric fluctuation at this point. And this thing, what I'm saying is a more general term, is a more general statement about the Hamiltonian and the theory of gravity. And in this case, it so happens that the Hamiltonian can be written as a constant times the integral of particular metric component HTT. Okay? So if you assume that your metric is the usual ADS metric at the boundary, and if you allow for fluctuations, and you read off the fluctuations at, this is in 4 dimensions, so it's, you read off the fluctuations at infinity, you read off the metric fluctuation at infinity, then you should be able to get what the Hamiltonian is. Okay, that's this statement.
Like how in asymptotically flat space, the Hamiltonian is given by the boundary integral.
Exactly. This is like this thing. By the way, this expression is true in something called the Pfefferman-Graham gauge, where you set your metric fluctuation to 0. But what you're saying is the ADM Hamiltonian, and exactly this is a statement of that sort. This is an ADS. In flat space, the statement was something of this sort. It's some component of the metric. It is like the Brownian stress tensor, I guess. Yeah. Right. It's also true for angular momentum and so on. You can write down all these conserved charges at infinity. Okay.
How will the observer at the boundary?
Yeah.
What sort of things that we have to do?
I'll come to that. I'm saying this is one of the terms, one of the statements that we'll use. The fact that the Hamiltonian is a boundary term and it lives on some particular time slice is what we'll use. I have not yet told you a protocol of how the observers in here will be able to detect what's inside.
How will you decode what is going on?
That I'll tell. I'll come to that in great detail. But for now, I'm just building up to the principles that we need. Okay.
So you written this expression in Pfefferman-Graham gauge.
Yeah. There's a more general expansion in any gauge where you have to use some other, I mean,
You cannot see that this will be a gauge where the Hamiltonian at least will be a gauge.
if you've just worked in the Pfefferman-Graham gauge, then I do not see how to immediately see that. But you can write down some more, you can, for example, there's one expansion that you can write down for a general lapse and shift and for some general HIJ. You do the 3+1 split because that's convenient to study these things at some time slice and so on. And you can write down an expansion which is true for any n and ni, any lapse and shift. And it's some similar expansion, and there if you just set the h or mu component to 0, it reduces to something simple. Okay.
Just a question. So far I have understood that you are getting the, due to causal effect, you will get the information at t equal to 5 from
Yeah.
t equal to 0. And you are choosing it with t equals to epsilon, and you are going to get the information at t equals to epsilon. You are saying epsilon tends to be 0. But don't you think this is an obvious question, because epsilon tends to 0 will exactly lie on the t equals to 0. The question should be that how big epsilon we can choose.
Sorry, so would you agree that if there's some excitation in the bulk, in here, if there's some excitation in the bulk, then I think it's non-obvious to say that an observer who is at the same time slice or something close by would know about this excitation. That is the non-trivial statement, and that's what we'll get to. The observer who is at some time slice which is close to this would know about the excitation inside.
And what is the reason behind, what is the motivation behind this principle of?
One thing is, well, I mean, in a sense, one thing you can ask is how general is ADS-CFT? Like what are the basic principles that goes into proving it? Like, for example, from ADS-CFT, of course, this is an obvious statement. Are you familiar with ADS-CFT? Okay, so from ADS-CFT, you would say it's an obvious statement because it's been established that there's some CFT dual which lives in here, and each bulk geometry with excitations that you write down would be dual to some state in the CFT. So from ADS-CFT, it would be an obvious statement. Our motivation in here eventually would be to see how this goes into flat space. Whether the same principles that we use in order to get this, the main reason we are discussing ADS first is it's just conceptually simpler. The same principles that you use, can it also be used in flat space, and to eventually see where or how the theory is holographic. Okay, any more questions about this? I've not come to the proof yet, or I've not talked about any sort of protocol yet.
Yeah, the question, I think the confusing part is the following.
Yeah.
Suppose there is an observer who is epsilon distance away from the boundary.
Okay.
Formal boundary, right?
Yeah, this
Yeah.
R tends to
So
infinity.
now, suppose you do a bomb blast inside, deep inside the ABS. Suppose there is a sun or something, some sort of thing, and then some fluctuation happens to that. What about the observer who is within the epsilon distance, not at conformal boundary? Because there you are saying that it is equivalent to, like, these two theories are equivalent, right? So whatever data you have on this Cauchy slice, on the boundary side, on the boundary Cauchy slice, you will have all the data that you require.
Yeah.
So this is fine. But as a physical observer who is close to the boundary but not in the CFT side, okay?
Okay.
So
This thing, you can also think of some observers close to the boundary, very close to the boundary, but not the CFT.
So that you are saying that even that observer
Will be able to decode it. Because I'll not use anything from ADS-CFT, everything that I do.
Yeah, I agree. But even suppose like something happens to sun right now,
Yeah.
it just disappears.
So
Will we know instantaneously?
if you could do measurements as accurately, you could. But because you see, because in order to make the sun disappear, you have to solve for the, okay, I was not actually going to talk about this, but the idea is that you have to solve for the Wheeler-DeWitt equation on the full time slice. So the sun disappearing, or the sun even being present at this point, is actually constrained because of everything that happens around it and so on. This is like saying that, I mean, the simplest way to see is, if you just had a simple, plus epsilon charge particle here, and if it suddenly became, you couldn't suddenly change this plus E to plus 2E without changing the flux at the boundary. That's the basic principle that goes behind. The same thing with mass. You couldn't suddenly change a plus m particle to a plus 2m particle without changing the metric at the boundary. If you did that, then your theory would not solve the constraints that you have.
The point is that all these changes are taking place instantaneously within some epsilon time gap.
Yeah, you can say some instantaneously. In a sense, in order to write down a consistent wave function, you'll have to ensure these changes happen. Is that an okay statement, or?
So this Pfefferman ground wave that you're taking HR.
Again, the thing will not be so important, but yeah, go on.
No,
Yeah.
but this gauge is also called like the holographic gauge. Kabat and Dinat wrote a paper.
Maybe, okay.
And they call it like holographic gauge because it preserves some holography.
Maybe for us, it's not important. This for like we'll never refer to the boundary theory. For us, it's just symmetric fluctuations as you go to the boundary.
But I was confused. I mean, if it is based on some holography.
No, this is not based on any holography or anything.
In this case, if you write the expansion,
Yeah.
subleading term it keeps having this. There is the metric and there is stress test, so you can directly read out from that.
Right.
The holographic stress test, so that's why probably they call it. Just from the metric expansion, you can directly read it out. The ground stress test, you can read it just from the metric expansion. And that's why it's just a name.
Yeah, it's just, yeah, I mean, I could have written down an expansion which is dependent on a general lapse and shift also. There's just a simple way to represent it because it's similar to the charge that we just saw there, which is proportional to the mass aspect at minus infinity. Okay, I've not even come to the main part of the talk, but this is the basic thing that I'd eventually like to go to and then argue as to how all of this would go into flat space. Okay.
Can I ask a quick question?
Yeah, please.
Because you motivated using the charges as well, right?
Huh.
So I have Gauss law both in gravity and in electro.
Good.
But you said that you need dynamical gravity for
Yeah.
whatever.
Yeah.
But so for some reason this thing does not work.
I'll just explain it. Just give me 1 second. Yeah. Good. So the thing that actually, thanks to Anisha's question, why would this thing have not worked in a gauge theory is your question, right? Or any other theory, and why is gravity important? And that's because in gravity, energy is positive, or the conserved charge is a positive quantity. Okay? That is not true in gauge theories. Like in gauge theory, I could have, it would not be possible for me to distinguish between a ball which has 0 charge versus a ball which has equal plus and minus E charge. It's some sort of, it's distributed in a spherically symmetric manner.
Universe where you have just positive charges, I mean, you just separate out the charges.
If you completely separated out and just had positive charges,
And negative somewhere else, and then you focus just on.
even then, I couldn't tell you whether there's going to be a simultaneous positive and positive negative pair creation or something. Because I can always create a pair of plus and minus charges. So this would be an obvious contradiction as to engage.
Region, the energy density.
If I allow myself to do dynamical gravity, if I allow gravity to be dynamical, I think what Anisha's question was, if I understood correctly, is that if you forgot about gravity completely, if you just had a gauge theory, just had QED or something, since I told that the constraints are going to play such an important role, would it also have worked in a gauge theory, just a pure gauge theory without gravity that I could measure everything from infinity? Then you cannot do it. That's the thing I want to say. That if you did not have gravity and if you just had a gauge theory, then you could not do it, and this would be one obvious counterexample. Because you could always have a pair of charges whose total sum would be 0. But you could not do that with masses. Because the moment you have one massive particle, some mass m, and you add another mass on top of it, it's always going to give you, something more. It's not going to decrease the mass.
But would the situation change if I have a gauge theory coupled to gravity?
The situation will change if you had a gauge theory coupled to gravity.
But then I can still have this sort of configuration.
Then you can have any configuration. So if your theory is sensitive to gravity, if you could measure these metric fluctuations at some order in g Newton, I think this goes as 1 by g Newton. There are some constants kept here, but if you could make measurements with this accuracy, then even if you had gravity coupled to a gauge theory or something, you could decode everything. That's right. Okay, any other questions on this? Yeah, feel free to ask anything, by the way. Yeah.
Can you repeat your explanation for why simple gauge theory will not work?
Huh.
You're saying some charges will pop up, plus minus.
I'm saying you would not be able. Okay, so the main thing that okay, this is. I mean, there are other ways of saying it as well. A physical way to see it is that if you had a ball of some charge, say just charge equal to 0, okay, and another ball which is not charge equal to 0, but somehow some nice spherically symmetric distribution of plus and minus charges,
Okay.
then these two situations would be indistinguishable from the boundary.
Why is that? If the electric field outside them is different.
The thing that you would have to measure would be Q's and so on, and the total charge in both cases are 0, right?
You can measure the multiple.
You can measure the multiple moments, but you can always ensure that you distribute them in some manner or the multiple moments fail. There's an even more formal reason for this, and another formal reason for this is if you compute some gauge invariant quantity like f mu nu, f mu nu. Okay, if you took some f mu nu, which was f mu nu at say this point x equal to 0, then this would commute with any observable at x equal to infinity on the same time slice. Is that okay?
You took a point, you took an operator.
At here, I'm just saying space-like operators commute. Space-like gauge invariant operators commute.
This
Yeah.
is locality.
Yeah. But in gravity, even this thing would fail because there are no local gauge invariant operators in gravity.
Right.
Any operator that you define that you might think is locally gauge invariant, you can always do a diffeomorphism and change it.
Yeah, you need that line.
The Wilson line or something, correct. So this is one more reason why it would fail in electromagnetism, or even in a scalar theory, for example.
So basically, you can't have local operators. That's why.
Local gauge invariant operators in gravity, correct. That is another thing that goes into proving it, yeah.
So that's why. Okay. All right.
Yeah, feel free to ask questions, because the things that I was going to say next are already asked in the questions. So yeah, just if there are more questions, feel free. Okay, is everything okay till here, or should I repeat some things? Or okay. Okay, so now if one is convinced that the Hamiltonian is a boundary term, then what would also be convincing is that this object is a boundary term. Okay, if H is a operator at the boundary, then even this object is an operator at the boundary. Is that clear?
What is that?
It's some number which tends to infinity. Okay,
Positive.
positive infinity, right? But this object is special because this is the projector onto the vacuum state. So, in a sense, if you this thing in here, only the operator that this corresponds to only picks up your vacuum state. Is that okay? Like that's the least energy state that you have.
Yeah, alpha
Yeah,
will
right.
have to be something like time, right? Because H
This can be anything. Alpha is, it doesn't matter what alpha is.
should have dimensions proportional to
Okay, it can have something like that, but okay. You can always put some dimensional factors to account for it. But yeah. But it's just something which will pick up the projector onto the vacuum state. By projector onto vacuum state, I just mean it's this guy. Okay? Is this point clear? Okay, good. Right. So the first thing is perhaps the most trivial question is that just given everything that we've got until now, suppose an observer was asked to determine whether the state in the bulk, let's call the bulk state as psi. Okay, there's some state psi.
So here massless excitations
In ADS it doesn't matter. Everything has a mass.
Oh, you are considering global area.
I'm considering global areas. Correct.
So you're assuming that the spectrum is sort of discrete.
I'll assume that the spectrum is discrete. And right. That's going to be a difference with flat space. Okay. Thanks for the question. Maybe I'll mention it right after this.
one comment just.
Yes.
There is an alternate quantization method in which you do take masses to 0. So usually we take masses to be positive.
You mean this m square lying between minus d by 4 and like this
Yeah,
thing in the
and we
BF
call
window.
and D something. Yeah, so there is another thing. What you are talking about perhaps is the standard quantization.
The usual standard quantization. Correct. Yeah. Standard quantization which have normalizable boundary conditions. If it's not normalizable, then it's like adding a source on the boundary, right?
Yeah, I'm not much aware about that.
Okay. But yeah, in this case, I'll just have normalizable boundary conditions. I'll talk about the spectrum in a second, but for now, I want to ask a very simple question. The question what one is asking here is, how does one know that psi is equal to the vacuum state? Okay? Like, how would one simply make a measurement at infinity and know that psi is a vacuum state? That's the question one is asking. And the answer to that is the observers at the boundary. So here, one should note that there's not just one observer at the boundary, but a set of many observers at the boundary. Okay? And this is where the no causality violation comes in. So notice that suppose a set of observers on the boundary have to measure the energy of the state. Say they have to measure the energy of the state, then there has to be an observer who is present at every point in omega. So if you think of this as your omega direction, then at every point in omega there has to be an observer present. That's how they'll know the metric fluctuation at every point in omega, and only then can they integrate this to get the full energy of the state. Is that okay? And since all of them at some time have only got the value of HTT at that particular omega, they'll have to meet at some point and then get the total value of the energy. And this prevents your causality violation. Yeah, feel free to ask questions if anything is not clear.
So that integral that you do,
Yeah.
you're interpreting it as the observers have to meet.
The integration that I'm doing is I'm interpreting that as a summation.
Yeah. So why is that?
I'm saying that each observer here would know the value of HTT at, say, some omega equal to 1, then this guy would be omega equal to 2, and so on. But in order to get the full energy, they'll have to meet at some point and sum up the result. Otherwise, nobody will ever know of the full energy that's present. The question that we're trying to ask is whether psi is equal to the vacuum state. And the protocol that we're going to follow is that they're going to make projective, they're going to measure the energy of the state.
Was psi the initial excitation in the bulk?
Psi is some excitation in the bulk. Okay, if it's the vacuum, then it's not really an excitation. But psi is some state in the bulk. And then the question that you're asking is the psi equal to the vacuum state or not? That's the most trivial question. I'll ask more non-trivial questions after this. But the most trivial thing you can ask is whether psi is the vacuum state. Is that clear? Okay. And the answer would be that they have to measure the energy of psi. Exactly. So in the vacuum state, the energy of the state should be 0, right? And so that means measuring the energy of the state psi is, by the Born rule, okay, measuring the energy of the state psi and asking the question, is the energy 0, is equivalent to measuring this correlator. This is from the Born rule in quantum mechanics, right? So this is an assumption that's going in. I'm assuming that the Born rule is true in everything that I do.
And you're calculating this correlator on the same time slice as psi?
Correct. Because P0 is an operator which lives on the same time slice. And in fact, it's a boundary operator. So the observers at the boundary formally have access to the energy of the state. But in order to know the energy exactly, they'll have to meet at some point. And that prevents the violation of causality. Okay. And the question is if this thing is 1, in this case, if this correlator is 1 with full certainty, then psi is equal to the vacuum state. Because this thing is simply mod psi 0 square. Is that okay? All I'm asking is if you've got a state in the bulk and asking if that state is the vacuum state.
Yeah, from boundary perspective.
From the boundary observer's perspective.
Yeah, and they are allowed to do measurements on the component of the metric.
They're allowed to measure the metric fluctuations at infinity, correct?
So, yeah, so when you say that they have to meet at some point.
Yeah.
So
That's to point out that there's no violation of causality in the theory. Or else naively it might think that any information, if it's present here, and the observers already know about it at that instant, then it might seem like a violation of causality.
yeah, exactly.
But
so can they, exchange information within epsilon time, or they cannot, right?
they'll take more than epsilon
Yeah.
time. So I'm saying formally all information is contained here. The way they'll be able to observe it is after epsilon time. Or after pi time, in fact.
Yeah.
Yeah.
Also then, then a single observer cannot.
Single observer cannot ever be able to get it.
Fine.
So if there's any...
You were thinking that, at least I was thinking that there is some observer at a particular point in the boundary. How long will it, whatever disturbance happened in the world, will this observer collect data to know the information about the disturbance?
A single observer cannot do this thing.
Yeah.
It's a set of observers on the boundary. Yeah.
So collectively these will have.
collectively they all have the information,
Yeah.
but in order to decode the information, they'll take some time.
Exactly.
But in principle, they have all information at some time. In principle.
Yeah.
Okay. Okay. Is this okay now or?
Yeah. Now it is.
Okay. Fine. Thank you. Okay.
This alpha finite and ask similar question for
Good. I don't think so. I mean, in principle, you could ask it for any general density matrix, but in this way, I'm going to be proving it is only going to be for a pure state. There are some other formal proofs we can give for any arbitrary density matrices, but that's not going to be. But that's not a protocol in a sense. That's just a formal statement.
if alpha is finite, so will you project
No, he's just saying that I think his question can be probably asked in this way. In this case, of course, you see the state that I'm taking is a pure state. I think what he's asking about is if you had some general density matrix, let's say.
the way you define this, I mean, if you take this alpha is like a beta e to the power minus beta is beta.
Sure.
So zero temperature is like beta.
Yeah, but the thing is, if you had a finite beta, then it would no longer be a pure state.
That's what I'm asking.
Yeah. You can generalize. You cannot generalize the step-by-step way of doing it, but you can give a formal statement that if you had any arbitrary density matrix, like any arbitrary density matrix of some form, C, I don't know, CMN, NM, some density matrix of this form, then you could decode these coefficients, or you could prove that the information about this is available at some time slice. But that's a more formal proof.
Alpha is not equal to 0, then it's not project the vacuum state on it. Then, because for finite alpha, this alpha 8 cannot be.
Then it would not project onto the vacuum state. That's true. I think what Avik was asking was, if you like this naively looks like you have some operator e power minus beta h, and then that would be some sort of a density matrix which is not pure, right? Density matrix not corresponding to a pure state. And so in that case, could you make general statements? Like that question is independent of defining the projector. This statement here is just defining the projector. Okay?
So you were saying that all the observers on the boundary
Yeah.
located at all values of omega, they would have to meet at some point of time to
Correct.
get the full value of.
Value of the energy.
So the minimum time that it would take before is probably pi, isn't it?
Yeah, it's probably pi. Yeah, because even they have to go from the boundary and so on. Yeah.
That time is also pi, and this time would also be pi. Does that prevent the violation of causality?
Exactly. This is what prevents the violation of causality. Had these observers just sat here and done nothing all the time, then eventually they would anyway have all information. This is like the Bob-Alice thing where you have these two spins which are entangled, and then Bob has to make a call to tell that I've got the upspin or something, right? It's basically the same argument of that sort. Okay, is this too confusing or is this fine? I mean, okay.
I don't, I'm not able to see exactly why it will be pi. How each observer, so there are infinity of them.
Yeah.
How each of them will be able to receive the information. They are
No.
the one measured.
The-
So that I am not able to see.
They will only be able to measure the value of HTT at the omega they are sitting in.
Yeah. So each of them measures their
Correct.
values. They get their values, and now at least one of them has to know all of them, all of the values.
I mean, or all the observers has to meet at some point, at some common point.
Send signals to.
Yes, some way, yeah,
Yeah,
at some
sending
particular,
signals or meeting directly.
something, yeah.
If they live on the boundary, or maybe they can move in the bulk.
They can move through the bulk or something, anything that you want to,
The bulk. Okay.
anything that you want
Then
to say.
they're traveling the short that distance.
Some way, yeah.
Okay.
Okay. So the idea is that if you, this actually tells us something more, that if you've got any state psi, and the observers measure the energy of the state psi and then ask the probability with which they're getting the answer 0, and if that answer is 1, like let's say they do this experiment 100 times, and if all the 100 times they're finding that the energy of the state is indeed 0, then the state must be the vacuum state. Okay? However, the kind of states that we'll be interested in are, of course, not as boring, but some operator x acting on 0. These are the kind of states that we'll be interested in, okay? Where these x can be any operator you want. So it's always convenient to represent a state in terms of operators which solely live at the boundary, because they don't have any bulk diffeomorphisms to play a role with. In a sense, what I mean is this: x can be a span of boundary operators. So if you can construct any boundary operator O, which look like limit r tends to infinity r per delta phi. Okay, and you can always construct a unique basis out of it. You can always construct a basis out of it, and then you can write down any state in terms of, like, these basis operators. Is that okay? Where these times vary in all boundaries. There's from any 0 to pi. These t's are in this entire 0 to pi region. Yeah, sorry, go on.
Yeah, so any state in the bulk.
Any state in the bulk can always be written like this. This is just from causality, because they'll eventually reach it. Okay. Okay, so now, of course, for decoding what these x's are, it will not be possible for the observers to do it by just measuring the energy of the state. We'll have to give the observers a little more power. Okay? And in order to do that, let me just take a slight digression and try and explain this thing in a much more simpler example, where you just have, say, a state which looks like this. Say I'm also taking any bulk smearing function. So say I have some state of this kind, psi, which is just written like this. This is okay. This is some bulk field, and this is some smearing function f of r. And the claim is, and you can put some lambda here, and the claim is that the observers will be able to decode what this f is, the function f is, by not only measuring along with measuring the expectation value of the Hamiltonian, they should also be given the power to measure the expectation value of the Hamiltonian and the boundary value of a field. Okay? So these are the kinds of measurements that they should be allowed to do. Is this clear? Where these O's are strictly some time interval 0 to epsilon. Is this an understandable statement? So what I'm saying is that the observers are not only measuring the energy of the state or measuring the expectation value of the Hamiltonian, but they should be allowed to measure correlation functions involving Hamiltonian and other boundary fields.
So when you say that the observer at the boundary can measure the energy, so that means they can only perform local measurements, right?
Observers at the boundary can measure the energy.
Okay. So this expectation value
Yeah.
calculation is together
For all the observers, yeah. So here I want to formally argue that all information is present at the boundary.
Okay.
That's the thing I want to formally argue for. And then we'll see how, like, in flat space it all just generalizes.
Okay. So and this gets okay.
So this is a toy example. I should mention this is just a toy example, which is a simpler thing from the previous case. And here I just want to motivate the fact that along with measuring energy, they measured correlation functions involving Hamiltonian and other operators. And other boundary operator at t belonging from 0 to epsilon.
All the expectation value calculations were performed altogether.
In a sense, yeah. Yeah.
They only need these 2 pointers.
They only need?
These
No, good. So it depends on how complicated this function is or how complicated the state is. In fact, for the flat space case, I'll give a very general algorithm in which they'll need a higher point correlator. But this, I mean, I actually give a protocol kind of thing. You see, this measurement is not a physical measurement in general because this, usually a physical measurement would be something where you would take a state and you modify it by a unitary operator and you then measure the energy. That would be a physical measurement, which I'll go back to in a second. But here I just want to motivate that if you restrict that physical measurement kind of a thing and allow yourself to measure arbitrary correlation functions, then and you allow yourself to not only measure the moments of the Hamiltonian, but the Hamiltonian and other operators, then you'll be able to decode the state.
So this perturbation in the bulk, it turns on some operator.
Turns on some. I don't need to worry about the CFT thing at all for now. You could think of all of this from a CFT language, but here I don't need to think of any CFT kind of thing. Here, yeah.
Multiplying with this exponential operator,
Yeah.
so is that
Okay, the exponential is just something. It just says that it's vacuum plus something else. It says that, yeah.
so does it keep it close to the vacuum?
In a sense, yes. It keeps it close to the vacuum.
That's
I'll just evaluate what, maybe, just give me 1 minute, I'll evaluate what this is and maybe that'll answer your question, yeah. Okay. So just to do this one example. So let's say we look at this guy, psi HO psi. What this turns out is that this is just equal to, so if we expand psi in lambda, so this is order 0 plus I lambda f phi plus order lambda square terms. And if you look at what this guy is, then this is 0 minus I lambda there should be a lambda. Okay, I've just expanded what these states are to order lambda.
Can you repeat the part about removing the restriction on allowing them to measure all correlations?
So this itself is a measurement which no physical observer can perform. It's just a statement that formally it can be performed. You know, formally you can evaluate all correlation functions, but physically you cannot evaluate all correlation functions. Physically, what you can do is you can modify the interaction Hamiltonian with some operator, like you're interacting with some system, so you can modify the interaction Hamiltonian with some object, and the object you modify it with would turn to the action of a unitary on that state. This is just perturbation theory. All I'm saying is that if you modify your interaction Hamiltonian with some system, then the way that would show up in perturbation theory is the action of a unitary on that state. Okay, so physically what you would do is you would take a state and you can act on it with some unitary operator. But if you do not restrict yourself to just performing physical measurements, then that would be any correlation function. There's probably some boundary measurement going on. So okay, I guess we're breaking for 2 minutes, so yeah, more questions.
Why is this small time fluctuation? 0 to epsilon?
It'll come up in the next step. But there's one more answer that you'll also allow yourself to measure momenta on the boundary, and momentum operator naturally requires a small time band. Yeah. Yeah.
Yeah, that was 0. Right?
What was 0?
Exponential acting on that. And then that was equal to 0.
Sorry, what? This is fine, right?
That was 0. My bad.
This was
It's
0?
actually multiplying that. So. that
Oh, I mean, this implies that size this. Would you be happy with this? Or?
that
Oh, okay, this thing was 0. Oh, okay. Indeed. Yeah. Okay. Yeah. You're right. This was 0 indeed. Yeah. Fine. Yeah. Okay. I don't know. Should I start or? Okay. Okay. So just for the star example, then what do we have? So we have some terms where the H acts on the vacuum state. We just assume that H acting on vacuum is renormalized to 0. So these terms would go away. And therefore, the only term that you would be left with would be in this. Okay. So the only term that you'd be left with through the leading order in lambda would be this guy. With the okay, that's it. This is the only term that would survive once you assume that H acting on vacuum is 0. So you have to choose your H in that way, that it subtracts of the vacuum energy. Sorry, what? Yeah, but at order lambda, this is the only term because the other term that you're saying would have 0, H0, F phi 0. So okay, what I'm saying is this thing. So if you write down the full thing, then the leading order term would be 0 HO0, which is 0. Then the next term would be minus I lambda. Plus the next term would be I lambda times F 0 H phi 0 plus order lambda square. Okay, and H acting on the vacuum is 0. So therefore, this term disappears, and you just have this one term. Okay. Now, what you can write this down is you can convert this HO to a commutator between H and O, which will basically give you O dot. You'll remove some factors of I, and you'll have some expression of this kind. Is that okay? Just nothing severe. And this is a bulk to boundary propagator with this phi at t equal to 0. This state could have been thought of as t equal to 0. And remember that I told you that these operators are allowed to go from 0 to epsilon. Okay? So this O can be also taken to be at t equal to epsilon. So this is a bulk to boundary propagator between these 2 points. Is that okay? And I mean, t equal to 0 is any point, some time, right? And this is at some r. If this phi is at some r, if you wish. You could have recast this completely in terms of a boundary operator as well. Then you would have had some boundary to boundary thing, which in flat space we'll see the expression is very simple. But yeah, in ADS is just a complicated expression. But the idea is that once you formally have this thing here, or once you have this kind of a 2-point function, then you can series expand this in terms of epsilon. Okay? Since this 2-point function is something that's valid at all epsilon, you can series expand it at in epsilon, and what you'll be able to read off would be the nth moments of f. You'd be able to read off any nth moment of f, and therefore reconstruct f. Up to, of course, given some accuracy that, if you have 2 functions which are the same after their 10,000th moment or something, then you'll have to make more precise measurements. But under some restrictions, you can always get this much information. Is that okay? I'll give a much more concrete example using a physical protocol, but this is a toy example where I just wanted to show that along with measuring the expectation value of the Hamiltonian, if you're allowed to measure the expectation value of Hamiltonian with other operators in the theory, with these other operators lying in the small time interval, then you can get all information out. So, so this state that I'm considering here, this phi's t argument can be thought of as 0. And this operator that the observer is measuring at the boundary, this t argument is say t equal to epsilon. So this is at some epsilon time. So the state is still defined in some thing, but the expectation values that they're measuring is at some epsilon. Is that okay?
So to get the full information, one has to integrate over all omegas.
In this particular case, okay, here I've just chosen a spherically symmetric function. So the omega dependence is kind of trivial. For a spherically symmetric function, it doesn't matter as to what omega it is. But you're right that in general, for the protocol that I'll just come to after this, you'll have to have all information at all omegas. Because you need to measure the energy of the state.
So in the beginning of the lecture, when you said that all information is available on the boundary within this epsilon time, it essentially means that it is available, like it is distributed on the boundary.
It is distributed on the boundary in some way.
You eventually have to integrate
Exactly.
something, and that you can't do without looking at something.
Exactly, which is what prevents your violation of causality. Okay, if I had colored chalks, then I could have perhaps told it in a different way. But okay, the basic idea is as follows. I can't use this board. I still can't use this board, right? Okay. I know. Yeah, it's just that it's too much work. This is completely useless. That's it. Sorry guys, just 1 second. So suppose you had some bulk. This is the ADS from a top cylinder point of view. Then if you had some bulk state which had some green stuff and some white stuff which was distributed in some weird way, then what it means is that anything which is available in this bulk slice is available on the boundary slice in some scrambled way, some weird way, whatever you want to think of. Or if you had some numbers here, let's say there was this number, some information in this which was 10101, then this would be available like this. Okay. Some information, each information about this is just getting scrambled at the boundary. And in order to completely construct the state, they'll have to meet and know that it's exactly this guy. Is that okay? Okay, good. Let me give the basic idea of this physical protocol then, and then go to flat space.
Just a second. So this if the observers are able to compute this expectation value of HO,
Then actually, the physical process will not involve that. But yeah, go on. Ask your question. Yeah.
So you said something about constructing moments of F.
I'm saying since you have this integral, you can always series expand in epsilon. So what you end up getting is some f with some other functions, which.
With O in the O dot.
Yeah.
Epsilon.
Yeah. So you know the expression for a bulk to boundary 2-point function.
These moments are relevant for showing what you want to show?
This thing won't be relevant, but all I wanted to say is that by measuring this thing, by tuning epsilon in some small value, you can get all moments of f. Therefore, you know the function f. You know the function f. This is like saying that you can reconstruct a function when you have all its moments.
Right, that's true. But,
Yeah.
So then I don't exactly see how I'm getting moments of f. So by series expansion of, so I need a probability distribution.
So this f would be like a probability distribution in a sense. In fact, this thing will become a little, this thing is a bit complicated to see from the ADS propagator, but in the flat space case, it'll be explicitly seen. How you get, so what you'd have, at least in flat space, what you'd end up getting would be some f of u, where u would be the retarded time, times you would get u power n by epsilon power n in some series expansion that you do. So which is what I'm calling the, actually I should not say moments of f, sorry, maybe that's confusing to you, but I should say moments of u with the distribution function f. This is what I mean. Okay. So these are the things that would come out of such measurements.
I think this correlator, if epsilon is a finite number, then also this is valid.
Epsilon, yeah, but the fact that it's also valid for epsilon being a small number is what makes it non-trivial.
If epsilon equal to 0, then
Epsilon equal to 0, then you cannot do the series expansion and won't end up with terms like this. What I would want to do is I would like to do a series expansion in epsilon.
from the coefficient of this series,
Correct. We'll reconstruct the moments. That's right. Okay.
This series becomes more and more convergent as epsilon goes to space, right? You can retain.
Yeah, I guess. Yeah.
So it feels like the lesser the time, the better it is to get the moments. But in some sense, it's only
Yeah, it's one by epsilon here. I think in the flat space it will be 1 by epsilon, but yeah.
here.
I mean, it depends on, of course, how much your restriction is. So maybe epsilon equal to 0.01 might be too high for somebody, and epsilon equal to 0.1 would be too high. Okay, but you can always rescale things such that epsilon is between 0 and 1, and you perform a series expansion. Okay. Anyway, so this was the set of a boring set of states, but and so what have we seen till now? So till now we have seen that if the observers are asked to ask the question whether the state psi is the vacuum state or not, they can do it in a simple way. All they have to do is measure the energy of the state, and after that I've motivated that along with measuring the Hamiltonian / the moments of the Hamiltonian, if they're also allowed to measure the correlation functions involving Hamiltonian and other fields on the boundary, then they can gain information about the state. This is of course not a protocol, as this is a toy example. You could have asked that, I could have taken a very complicated example of a state, and then this correlator would not be enough. One could have easily tricked you into that. So now what I'll try and convince you is that there's a physical procedure by which you can actually decode this in EDS, and I'll explain you how to also do that in flat space. So for simplicity, let us now ask the question that what is the or let's say I'm not sure how to frame this. 1 second, please. Okay, so H and O's commutator will give you O dot. H is the generator of time translation. So
In what sense are we simultaneously measuring all these correlators?
simultaneously measuring all these.
So they will have to simultaneously keep track of all these correlators.
No. The observers at asymptotic infinity won't have to keep track of these correlators. I'll talk about the correlator they have to keep in track of in a second. But the observers at infinity have to, just give me 1 second, maybe the next step will answer your question. But the physical protocol will not involve the observers measuring this guy. This is just a toy example to show that if you allow yourself to measure arbitrary correlation functions with the operator insertions being in some small time interval, then they can gain all information. But this is not going to be the physical way in which they do it. Okay, so the physical way will be as follows. So we asked already if, so the question that is answered till now is psi equal to vacuum. This is answered. But now the question that you can ask is psi equal to x acting on vacuum, where x is any basis state operator. Okay, if you have constructed some basis, a set of basis, if you've constructed some set of operators which form a basis at the boundary, then you can ask if psi is equal to this. Okay, and the way you do it is that you allow yourself or allow the observers to not only measure the energy of the state, but also modify the state with some unitary and then measure its energy. So these are the kind of measurements that the observers have to perform, and that's it. These will be the only kind of measurements that the observers will ever have to perform. They should allow themselves to act on the state psi or modify the state psi by acting on it with some unitary operator, and then measure the energy of that full state. Is that okay? P0 is the projector. So this basically answers the question. The value of this the value of this correlator is basically answering the question that what is the frequency with which energy of u psi is 0. This is basically asking you this question. And by the Born rule, it's basically this guy. In fact, I should say it's. Why do we want this? I'll just literally tell you how you'll be able to tell whether this is equal to this by measuring this. I'll just come to the next step. But I'm saying these are the set of things that you should allow the observers to do. So the observers are allowed to measure the energy of the state and also measure the energy of a state when it's acted by an unitary. And these unitaries are living in some time band 0 to epsilon.
So I have this x.
Yeah.
And my question is whether my state is x0.
Correct. And these will be the kind of measurements that they have to do. I'll give you a flat space protocol right now. In fact, everything that I've told till now can just totally be put in flat space as well. Instead of writing down some basis states on the boundary of ADS, you could have written the basis states at null infinity, at all of Scri plus, and you could have asked the same question. P0 as of now, I'll project onto one particular vacuum. Good. I'll talk about the vacuum degeneracy issue towards the end, because that's something for which we don't understand a physical protocol way of. But there's a formal statement, but I'll say that towards the end. Yeah. But X is any basis set of any set of basis operators. In fact, there's this statement that you can by okay, I'll not use the statement, but let me just say it because it's a more general version. There's a statement that you can construct any state by acting with x's which lie between 0 and epsilon, acting on the vacuum state. Any state in the Hilbert space can be written in this form. Okay, and this thing goes by the name of Riesz-Leiter theorem, but I'll not talk about this. I guess somebody's talking about modular QFT. Will talk about this a lot more. Yeah, you'll probably talk about this a lot more. But I could have also recast this thing into a more formal statement of this kind, but I'll not go to that. I'll give you a more practical way of writing this in a second, along with answering Anish's question about vacuum degeneracy zone. But yeah. So the kind of states that that I'll actually write down for you will be of this kind. So the kind of x's that I'll be dealing with would somewhat be of this. I'll explain what this condensed notation is in a second. So this, the way I've written it is in flat space, but I could have exactly equivalent in ADS as well. So what this expansion does for you is that it talks about any state of this kind. It has got some G1, U comma omega, some phi, U1 comma omega, du d omega, plus this whole thing, plus say G2, U1, U2, omega 1, omega 2, plus so on and so forth. Okay, all of this can collectively act on the vacuum state. You can just replace the U's with T's and think of this in ADS. Okay, but this is any state that I could have written down. Would that be happy with any state which has zero overlap with the vacuum? But that's not important. I can always ensure this is maintained. But as of now, this is a very general state that I've written down. Okay? And yeah. No, I said that. So here I wrote that the next kind of question that we'll ask is psi of this form, x acting on vacuum. So I'm saying that if your x was something very general, which is some sort of a state like this, so these are just denoting normal ordered products. So the double dots are just normal orderings. And these G1s and G2s are any smearing functions. So if you're in ADS, you'd have just put T's here. And these G's could be any function from 0 to pi. G's could be any function. Here, if you were in flat space, then these G's could be any function in any function in here, at the full of all of Scribe plus. Is that clear?
Is this part on the null infinity?
This part can be, I mean, you can think of it as both on null infinity or in ADS. Like in ADS, I would have to just put T's instead of U's. At null infinity, I just have to put U's. So any state which has massless excitations in flat space, I can always write in this form. But in ADS, I could have just done it in general, without assuming massless or anything.
And you're going to restrict it to 0 to epsilon.
I'll come to the 0 to epsilon part very soon. But I'm just saying you can parameterize any state in this form. And what I'll now give you is a protocol for decoding G1s, G2s, G3s in a systematic manner by only restricting to measurements made between 0 to epsilon. 0 to epsilon here, or in this case, u equal to minus infinity to u equal to minus 1 by epsilon. Basically at scribe plus minus. Okay, I'll tell about why this thing is important, but in ADS case, it's from 0 to epsilon. Is that clear? So this is u in ADS, and in here it would be, yeah, sorry, somebody asked a question. So if I'm in ADS, which I've been till now, in ADS, for example, this integral would have been like this. This would be the u. Whatever I was calling time, I'm just writing it as u now. But I could have also done it in flat space. I could have also written a very general state in flat space, only consisting of massless excitations, such that these integrals are over all of Scribe plus. All these ui's belong to all of Scribe plus. Okay. Any other questions on this? Okay. And the claim is that if you use un's of this form, so these u's that I wrote down, if you use u's of this kind, I'm writing these u's are any um's, which are exponential of I. So this I'm writing in flat space, and in ADS, the same expression would hold, but with times being 0 to epsilon. The same expression would also hold in ADS, where you'd use exponential from I from 0 to epsilon now, and du prime, d omega prime, and so on. Same thing. So these are any unitary operators that live on this small time window, either 0 to epsilon here or minus infinity to minus 1 by epsilon here. And what these unitary operators look like are basically, let's say for the simple case of when you've just got one operator or something, it's something like e power I times some function which you know of. So the fn's are up to the observer. The observers can tune whatever fn's they want to tune, and they are basically unitaries of this kind. They are any real functions, in fact. Fn's are any real functions, but these g's can be any complex. Is this clear? So these are the kinds of unitaries that they'll act with. The observers at in this time interval 0 to epsilon, or the observers at the time interval minus infinity to minus 1 by epsilon will act with. So M as in, I'll tell you that if you measure this, I'll just come to it in a second, but the idea is that if you measure it for 1, you'll be able to get G1. If you measure it for 2, you'll be able to get G2 and so on and so forth. I'll recursively do that. Yeah. Is this clear as to what unitaries they'll act with and so on?
I mean, those are the axes,
These are like the x's.
and these are the corresponding views.
These are the corresponding u's. These are the corresponding u's that they should choose. It's some compact notation for a unitary of this kind. It's some F1O plus F2 O1 O2 and so on, where these F1, F2 and these functions are basically smearing functions in this small time interval 0 to epsilon. And these are up to the observers to tune. They can choose whatever smearing function they want between this time interval 0 to epsilon, or in flat space between the time interval minus infinity to minus 1 by epsilon.
I'm not able to see the correspondence. So over
Which?
there you have G's.
I'll come to why this is helpful. For now, I'm just writing the unitaries that the observers will act with. So the observers will act with these unitaries on the state psi, and then they'll measure the energy of the state psi and ask whether the energy is 0 or not. Okay, is that? Yeah, this is an integral of omega prime. So these are basically some smearing functions which is up to the observer. I could have as well just set it to 1. Doesn't matter. Why should it have? No, so since the observers are acting with these unitaries, they are the ones which will have this u prime and omega prime. So the variables that the observers act with are denoted as u prime omega prime, lying here. O has, again, just u prime. So this, these are all integrated over, by the way. Yeah. Yeah, okay, these should be omega primes. So that's, I mean, they're all primes. So I mean, and of course they're integrated. So the observer a priori does not know about what the state is, right? A priori, this thing should have no information about what the G's are. So corresponding to a set of G's, you'll get a particular state. So is that clear? Like, feel free to ask more. I mean, I'm almost nearing end, so yeah, feel free to ask more about this. So is that, do you have a question? So, yeah. Oh, no, I mean, this is just a collective way of writing U1, U2, U3, and so on. That's it. Sorry, yeah, maybe I should have mentioned this. So these guys are just collective way of writing U1, U2, U3, and omega 1, omega, so on. That's all these things are. It's approximately local, yeah, between the 0 and epsilon window. Okay? Okay, great.
Your notation, so O is always under the limit at
Correct.
not a general weird operator or anything. It's always under the delta.
Yeah. O is always the boundary value of the operator, like the extrapolated operator. That's right. And even in flat space, O would be a similar thing. You know, the similar R, like the R stripped off version of the bulk operator. Like you take your bulk operator. Let's say you take some phi bulk, which is a function of u r omega, and you take limit r tends to infinity, r power, in flat space it's just r here, that will give you O, u comma omega. That's what O's are defined. And in ADS you'll have to define with r power delta here.
Right. So in ADS there's a clear distinction between like the growing and the normalized and the
Correct, yeah.
there is no such thing, right? Like,
Yeah, I don't know of anything, yeah.
so what is the motivation that you define this? Like,
One motivation is that if you just look at the stress tensor, for example, then the stress tensor would, in these O's, in terms of O, is just del U O, del U O. So, I mean, it's like you know, the energy has to be finite. So that has a R squared term, R square multiplying del mu phi, and So the phi should fall off in this way.
So, so you have an index over f of m is there,
Yeah.
which has an index m.
It's not okay. It's not a. Go on. Go on. Yeah.
So, and then you're taking a product of m times.
Yeah.
So does f
Yeah.
m multiplied m times?
No. Yeah. I could have put this f here. This I could have put the f outside the product.
Okay, it's not. In the
Yeah. It's not. It's not in the product. Yeah. You're right. Thank you.
That is smearing comes first and
Right now it's in the product.
No. It's. You can just put it outside the product. F's are just outside the product.
it's a different rate in the exponential, it's you have F1, F2. So
Uh,
that also carries some index.
That would carry some. 1 second, please. Sorry. So good. So maybe I should write this in a bit more clearer fashion. I've written it wrongly here. So these u1s, for example, would just be e power I f1o. u2 would be e power I f1 f2 u1 u2 omega 1 omega 2 times o of u1 omega 1 o of u2 omega 2. Is this okay? And similarly for u3 and so on. Sorry, is this fine? So these are the unitary operators that the observers would act with, where these u's are in for the flat space case. These u's will be close to square plus minus in flat space, and in ADS, these u's will belong to 0 to epsilon.
All right.
Is that fine?
Yeah.
Okay. Good. So if we do an example where the observers now specifically compute this guy, psi u1 dagger p0 psi u1 psi, okay, with psi equal to this full thing here, right? Then that thing is basically would reduce to this guy. This is something you can get by just expanding this up to order f. So for example, these u's have f in them, right? So I can expand this unitary as 1 plus I f1o plus order f squared and so on, okay? And I compute this thing up to the least order in f, so this will be valid up to order f cube. Is that okay? All I've done in going from this step to this step is done something very similar to the toy example where I expanded the unitary and computed this expectation value. Is that fine or? Okay. Good. So what this tells you is that okay, now this object on the left-hand side is basically a physical question that the observers can ask, which is that they modify the state with some unitary and then ask the frequency with which you get 0. So it's always a number. Okay, it's always some number that you would end up getting. And the object on the right-hand side should eventually tell us what this function g's are. Okay, so these are the things that depend on the state, and these are smearing functions up to the observers.
Why are you calling it frequency? Probability.
Yeah, okay, it's like, okay, if you measure it 100 times and then 99 times if you get 0, it's just 0.99. That's the kind of thing I mean, yeah.
What happened to the order x to the 0?
Order f to the 0. You mean the term with just 1?
Yes.
So in the way I've written the state has no overlap with the vacuum. So therefore, that first term goes away. And in general, you can show that you can always write down a state in this form without an overlap with the vacuum. You can always do a small measurement at infinity. You can always tune 1 degree of freedom at infinity and make sure that happens. But yeah, I could have gone through that proof, but it's just a bit tedious. But is this fine?
Yeah, so order F, few terms and
But then since these f's are smearing functions up to the observers, they can tune up to what order they want to study it. Like I could have chosen, the observers could have chosen f equal to 1 by 1000, and they could have only restricted to measurements up to order 1 by 1000 square. Yeah. You mean, that's because you see, in the state that I've, the way I've written psi here, the psi is actually something which starts off as, so the psi starts off as, okay. Sorry, this is G. Plus 1. This is the way I've parameterized psi. I could have chosen a more general parameterization where psi could have started with 0 plus something in here, but it can be shown that you can always remove this term and choose it like this. So the 0 is not going to play a role. Like I could have also chosen a more general term and first argued that I can remove 0 by acting on it with some unitary, and then always put psi in this basis. So once I've put psi in this basis, this clearly means that psi overlap with the vacuum is 0, just from construction, as these are all normal ordered products, and hence you just end up getting this. Is that okay? Okay.
Fm, for example, corresponds to the smearing function for product of M operators.
That's right, yeah.
So now, how do I know their contribution will, the product, like the higher the product, the lesser their contribution in this?
Okay. Maybe let me just go through the proof of this. So for example, if we question is, I guess, how did we get to this? Where did all the other GNs go, I guess? Because
Also Fs.
F's don't come in because I just have one U.
Oh, acha.
U1.
This is
Okay.
fine.
So no, but one thing that you could have asked is where did all the GNs go?
So there you had some lambda, right?
No, I'll just explain how this comes in. So you see, psi, the general state psi is this. Okay. So if I just expand what this guy is, then this is 0. It's a normal ordered phi u plus, this is G1, G2. And so on, whatever else you wanted to write down. Times you've got your unitary U1 dagger. So your U1 dagger would be 1 minus I F O. That's it. P0 times 1 plus I F O times psi again. I'm not writing the same. Okay, maybe I'll just write it here. D omega times, this should be G star. Okay. Till this step, I've done nothing. I mean, these are also going on to higher points. So now what I'll, and this P0 is basically 0, 0. Is that fine? So now what I'll use is that since these are all normal ordered operators, okay, so what I'll use is the following statement. If I have some normal ordered operator phi 1, phi 2, phi 3. And if I just have O1, O2 here, then this is 0. Okay, because these simply have more creation operators than the annihilation operators. Okay, and it is precisely because of these kind of or this kind of a what do you call it? This kind of an identity where there are less number of creation operators as compared to or the opposite, the less number of annihilation operators as compared to creation operators, that for U1 you would only have this G1 which comes here. Whereas had you used U2 in here, you would have had G2 coming in here. Is that okay? Yeah.
Other than the fact that you are using the vacuum part, it also uses the fact that phi, the 1-point function of phi is
1-point function of phi is 0. Yeah, that's something I'll assume. Yeah, because phi can be written in terms of A and A dagger.
this expression will contain terms like expectation value of phi, right?
Uh, yeah, sure. Yeah, I mean these are, yeah, sure. We'll use the fact that 1-point function of phi is 0 in the vacuum state. Yeah, I think that's a reasonable assumption. This is a what is this called? The normal ordered 2-point function. So that would be 0. Okay, and in this case, the thing that allows us to restrict this guy to simply this expression is identities of this kind, since you've got less number of annihilation operators as compared to creation operators.
We must have equal number of O's and
Exactly. And what would happen is that if you had allowed yourself to measure UM dagger POUM, then you would have picked up a sum of terms where the last term would have been GM. Okay. By the way, how much more time do I have? Probably almost done, right? Or, okay, sure. I mean, I'll take about 15 minutes more, but we can break